We're going to keep studying reactions of alkyne, and this time we're going to be doing what I have here on the screen, which is hydrogenation reactions. Before we study hydrogenation of alkenes, I'm going to write it here. So alkenes, was like that. Say, for example, and we added hydrogens across the double bond. So that was our hydrogenation reaction. So one condition, for example, hydrogen with platinum or palladium, and here you will have the following alkane. Now, in the case of alkynes, we say we will have more options. If we use the same condition, and we do the hydrogenation of using hydrogen with platinum, then it will fully hydrogenate, and so across, say, one double bond, the other, you say it continues. Alkene, and then alkane. So at the end, you're going to get butane. So you're going to add here actually 2 moles of hydrogen, right? So here you added 1 mole, 1 hydrogen across. So, but adding 2 moles, or you can say in excess, we would produce the alkane. Now, what if you wanted to have the alkene instead? So there is a couple of conditions that we can use to do that. One is using a poison catalyst. And one poison catalyst that we have is Lindlar's catalyst. You may see this when you do problems as written with formulas. I'm going to write it down. What Lindlar catalyst is, so let me circle that. Lindlar catalyst will have quinone, here, it will have palladium and barium sulfate, and that's with metal. So that is what we call Lindlar's catalyst. Most likely you're going to see it like Lindlar's, but just in case you see this, you will know it's the same. What this does is poison, in another word, it catalyzes the first reaction from the, say, adding just 1 mole of hydrogen across the triple bond to make the alkene, but it does it in a way that the product is a syn alkene. So it adds the hydrogen to the same size. Say, well, let me draw it. It added it here, like so. So this is a cis to butene. And again, it is because it's a syn addition to the same side. But that's one possible stereoisomer. But how if we wanted to make the trans? So in that case, we will use another condition. So that's a metal, sodium, and ammonia. So in the mechanism of that, let's draw the final product, but why do we get the trans alkene? So our final product is that. This is trans to butene. But the idea of why we get here trans and what we get using Lindlar C. So, but why this? Why this is trans? So when you have your alkyne here, and let's remember that sodium, I'm going to write the electron configuration here, is number 11 in your periodic table. Let's make it another color. So you say the electron configuration would be 1s2, 2s2, that's an S, 2s2, 2p6, 3s1. What that means is that you have on this 1 valence electron. So I'm going to just throw that electron. So this reaction is via radical. So in radical reactions, we will write fishhook arrows. So we're going to do this, so one side. So fishhook arrows are like that. This means we're moving 1 electron. So here, 1 electron from the sodium, and of course, sodium is oxidizing to sodium plus, which is isoelectronic lithium. And here you make in, say, an ion, and the other electron will go here. But now this needs to be fishhook as well. All right. But notice if you create an anion here in a radical here, you will have electrons and they do repel each other. So the best way to have that is to put the electrons away from each other. So if you have that, let me just, I'm going to draw those, say, with orbitals. So now they are far away. And that's better than having them close together, let's say, lower energy. And that already dictates that the product is trans. In the next step, what you do is an acid-base reaction. So when you have an anion, and if this is done, the solvent is ammonia. So what you have is a proton transfer. So you will have, say, ammonia. Let's throw 3 of these. Plus, so acid-base reaction. So proton transfer. This time, I'll use the other arrow. And the product of that will be a radical. Now I have added a hydrogen, and I will have a metal here, and I still have a radical. What happens next is another atom of sodium will transfer 1 electron over here, and that 1 electron, you will create another anion, and then another proton transfer. But the key point here that determines actually the stereochemistry of the reaction is the first 1 electron transfer. When you do that, you want to have the configuration in which the pair of electrons here is opposite to the electron in the radical. So the radical anion, intermediate radical anion, already dictates that the geometry of the product is trans. So summarizing, we have 3 methods when we are doing hydrogenation of alkenes. If we use hydrogen with platinum or palladium, we will not stop at the alkene. It will continue to the alkane, and we get here in this example is butane. But if we want to get the alkene, we have 2 methods, and what you use will depend on what you want to get. If you want to get the cis alkene, then you use the hydrogenation with a poison catalyst. In this case, we have Lindlar's, and here is the formula in case you see this instead of the word Lindlar's in the reaction that you're doing. And the other reaction that we need to remember is the condition to get the trans alkene. So it's always going to be a metal. This is an alkali metal and ammonia.